In this video, we'll be talking about Green's theorem for complex variables. And you might remember something about Green's theorem from multivariable calculus, maybe just that it's something relating areas to perimeters and something about the integrals about both. But we're going to make it concrete for complex variables, and if you go back to your real variables definition, you'll see how they're kind of linked. Okay, so let's just kind of put all the parts together first and see what conditions must be met. So first, the purpose. What is the purpose of Green's theorem for complex variables? It's going to be to try to, in some cases, help us work out the line integrals that we were working out in previous video. So it might help us work out this in certain cases. So now let's see what has to be true. First, for our gamma has to be a smooth, closed, simple, and for these three definitions, go back to the previous curves video and just recap if you need to, and it also has to be positively oriented. So what does positively oriented mean? Remember, that means that if we have our gamma, then it has to, as you travel along gamma, you must always keep its interior on your left. So in this case, you go counterclockwise. And this interior, we're going to be calling uppercase omega. And uppercase omega will be a domain. And if you go back to the sets video, or if you remember, a domain is an open connected set. So this omega is just the interior that gamma is enclosing. So it doesn't include gamma. So omega is a domain, and you can kind of call it an area. And gamma will be this smooth, closed, simple, positively oriented curve, which you can call a perimeter. So now a small technicality to note is that gamma does not have to just be one piece. Gamma can be multiple pieces. For example, let's look at this example. Now let's say omega is just this part of the kind of donut. So if omega is only this part, and gamma is these two curves, it's this outside curve and this inside hole. So now we have to see which direction it's going. The outside one is going to be going counterclockwise as usual, because that keeps the inside on the left. But the inside one must be going clockwise, because only by going clockwise, then you keep the omega always on your left. Okay, so sometimes you might see domains with holes in them. You just have to be careful to always put the inside curves going clockwise, the outside curve going counterclockwise. Okay, and the last restriction that we have to do is actually on f of z. So f of z, let's say we can write it as u plus I v, where u is the real part and v is the imaginary part of f of z. And these are both functions of x and y respectively, if z is x plus iy. Now, what has to be true? It has to be true that du, dx, du, dy, dv, dx, and dv, dy are all continuous on D. And D is kind of a bigger domain, like a father domain, like a domain that contains gamma and omega. So for example, if this is gamma and omega, then D might be a domain like this. And remember, it's going to be open, so it's the open domain that's all of this in here that contains gamma and omega. Or it could just be the whole complex plane. It could be as big as small as you need it to, but the only condition is that it must contain gamma and omega. And all these partial derivatives have to be continuous on D. And usually it's not really a problem to check for that, because if these are just polynomials, then they're going to be continuous because polynomials are continuous. But if they're not polynomials, then that's a heads up for you. You might want to check that out. So now, if all these conditions on this paper are met, so these conditions about gamma, this condition about omega, these partial derivatives continuous, then now we can formulate Green's theorem. So we'll do it on the back of this paper. We'll write it pretty big. So Green's theorem says that the line integral over gamma of f of z dz is equal to I double integral over omega now df dx plus I df dy dx dy. Okay, so I'm going to put a giant box around it. And this is Green's theorem for complex variables. So it does look significantly different from real variable definition, especially because there's all these i's floating around here. But there is a way to equate them. So we won't go into that technically here, but they are equivalent definitions. So we see how this is an integral over the perimeter, gamma, or the curve, the outside curve. And it's linking it to the double integral of this area, or domain as we're going to call it. So this seems pretty intimidating, but let's work it out in an example and see how it's actually pretty helpful. So here's my example. We want to compute the integral over this gamma. So the gamma in this case is a square. So this is 1, this is I, this is -1, this is negative I, and this is a square of length 2 because it's 1, 1 in each direction. So we want to compute the integral over the square of modulus z squared dz. Now, we don't need to use Green's theorem for this, right? You can just use the techniques we learned in the previous video. So how you would do that by, you would have to designate this as curve 1, this is curve 2, this is curve 3, and this is curve 4, because they're all kind of disjoint straight lines, so you can't have one curve that describes the whole square. And then you need to take the line integral over piece 1, over piece 2, over piece 3, over piece 4, and then add them together, and then you'll get your answer. And I've actually done that here, and you can see it's very, very, very messy. So I had to take curve 1, curve 2, curve 3, curve 4, parameterize all of them, and in each case I had to kind of rewrite the parameterization because there was a modulus involved, so I had to get the real and imaginary parts. And then you see I did integral for 1, 2, 3, 4, and in the end my answer was 0. Okay, so I got the right answer, but it took all of this work. So now we're going to ask ourselves, is there a way we can use Green's theorem to make this a lot easier on ourselves? And the answer is yes. So let's keep Green's theorem here handy just for reference and think about how are we going to do this. So this is the integral we would like to evaluate, and we need to kind of just plug everything in this form. So let's put it in this form right now. So we're going to write I double integral, and it's going to be df dx. So now the first challenge is to write f in terms of x and y. So what is f? F equals modulus z squared. And z is what? X plus I y squared. And what is modulus of x plus I y? Well, it's going to be x squared plus y squared radical. And we're going to square it, so the radical goes away. So here we've successfully written f in terms of x and y. So now we can have df dx is going to be 2x plus I. df dy is going to be 2y. And we're going to have dx dy. So it got a little bit cramped there. So let me draw a line. And now what are the limits in terms of x? So that's going to be -1 to 1. What are the limits in terms of y? That's going to be -1 to 1 again. So don't confuse yourself. The limits of y are not going to be -I to I, because y is the real number that's in front of I, right here as we see. It's the imaginary part. So each limit is from -1 to 1. So now this is not too bad to evaluate. Let's try to evaluate it. So it's going to be I integral -1 to 1. Let's evaluate the inside one. So 2x with respect to x is x squared, and then 2iy with respect to x is 2xyi. And we're going to evaluate that from -1 to 1. So let's forget the integral really fast. Let's just evaluate this inside integral. So that's going to be 1 squared is 1 plus, and then 2 times 1 is going to be 2yi minus, and then we're going to have -1 squared is 1, and then we're going to have minus 2yi. So this, when we do it, comes out to 4iy. Okay, so now this inside integral we worked out is 4iy. So now let's work out the outside integral. So it's I -1 to 1, and it's going to be 4iy dy. Okay, so this I is a constant, or this 4i is a constant. We can take it to the outside. So 4i times I is -4. So we have -4 integral -1 to 1 y dy. This is going to be -4 1/2 y squared -1 to 1. So it's going to be coming out here. It's going to be -4. And then when we have 1/2 1 squared minus 1/2 -1 squared, that's just going to be 1/2 minus 1/2 is 0. So it's going to be -4 times 0 equals 0. So sorry if this was kind of messy. I didn't mean for it to get this messy. But if you want to work it out for yourself, it shouldn't be that bad. Or just follow what I did here. And you find the answer is 0. And that took considerably less work than tediously going through curve 1, curve 2, curve 3, curve 4, parameterizing them, making an integral for each of them, adding them together, and you get the same answer in the end. So just kind of a heads up is you want to use this when you kind of have disjoint pieces that you think are going to take a long time to do individually. Then it doesn't hurt to give Green's theorem a shot, and maybe you'll get lucky here and you'll get the right answer.